Let's continue talking about the type of electrolytic cells from the endpoints. We, in the previous lesson, in the point of structure of the electrolytic cells, we previously studied that the structure of the electrolytic cells consists of two main parts, which is anode and cathode, two electrodes, supply by a power source or electric source, which is battery, negative pole of the battery connected to the cathode, and the positive pole connected to the anode. And both of them are embedded inside electrolyte solution or molten. So those are main parts of the electrolytic cells. Before classifying the electrolytic cells into many types, we need before to know its application, its industrial uses. When we know what its uses, we can specify each type from its classification in a definite uses. We can know we need this type of electrolytic cell in this purposes or in this industrial uses. It can easy to make link. So the uses or the purposes which we use electrolytic cells for it may be purifications for metal, one of the purposes, may be separation of solution. May I have separate a solutions particles, its positive and negative particles, may be metal, extracting like aluminum, extracting from its ores, and maybe also for plating, metal plating, as we will know later. So all these purposes and uses we use it in electrochemical cells. Sorry. So what is a type which help us to use all these purposes? We can classify the electrochemical cells into according to two main factors, which is the type of electrodes, and type of electrolytes itself. That means that I can make 4 different types of electrolytic cells. The first classification is may I have in electrolytic cells 2 similar electrodes. When I use 2 similar electrodes, like as we can see, we use 2 graphite electrodes made up of graphite or made up of platinum. 2 similar electrodes, which is chemical reactivity is low. We then make inert electrodes. Inert meaning it's lazy. It's don't share in chemical reaction. It don't share in the redox reaction, which will happen in the electrolytic cells because they are similar electrodes and they lower activity. They low in activity and don't share in the reaction of the electrolytic cells. So they called inert electrodes. And we can guess here that this type of electrolytic cells, we will aim and focus the electrolytes of it. We will make the reaction on its electrolyte solutions, not to its electrode. And the other type is active electrodes. Maybe I have active electrodes like the electrolytic cells of zinc and copper, zinc electrode and copper electrode. Both of them have different degree of reactivity in chemical reactivity series. So they make reactions, redox reaction. So the action of the electrolytic cells happen in its electrode, because the zinc and copper, for example, magnesium and iron, for example, have different reactivity. They are different in electrochemical activity, so they make reactions, reduction and oxidation, so they call the active electrode. So when we have a similar electrode lower in activity, like graphite or platinum, we have here inert electrode. And even when we have active electrodes, two different electrodes and in their reactivity. So here we have active electrode, and the redox reaction will happen at the two electrodes. Then let's see the second classification for the electrolytic cells. The second one is the type of electrolytes. We agree that the electrolyte is made up of ionic compounds that can contain free ions, but it can't contain a free ions even it was molten. The first form or probability for the electrolyte may be molten, like NaCl molten, or even aqueous solution. Let's ask the question, why we classify those two different states as two different states? Why we don't consider them a one state? Because each one of them will give a different result in electrolysis process. The molten of NaCl in electrolytic cells will give a different result than the solution in NaCl, the aqueous solution in electrolytic cells, and we will see later. So we can classify the electrolytic cells into four main different categories, which is have inert electrodes or active electrodes, and the other types which may have molten electrodes, electrolytes or solution, aqueous solution. Both of those cases will give a free electrons, but not the same result in electrolysis. So let's take an example or show an example for what's happened at the two electrodes of the electrolytic cells. We have here electrolytic cells, which consist, like we mentioned previously, from cathode and anode. It consists mainly for two electrodes, cathode and anode. Here we have two similar carbon. We have two similar carbon electrodes, so we called it inert carbon electrodes. Inert carbon electrodes, here we can conclude that the redox reaction or the chemical reaction which will not happen to the electrode, it will happen to the electrolyte itself. It will happen to the electrolyte itself. And as we can see how the battery, the positive pole of the battery, forces the carbon which connected to it to lose its electron, to transfer its electron to the other side, and decreasing the electron charge on it, changing it into positive electrode, which is called anode. And the other electrode, which is called the cathode, increasing its negativity charge of electron, and it change into negative electrodes. So here, it is the mechanism of which each electrode is changed into its charge. The anode takes the positive charge by giving the electron to the cathode. So we need in the container here to contain like a molten solution, molten ionic compounds or aquatic ionic compound to allow the electron continue transfer to the other side, from the cathode to the anode in the solution. So the electron transfer from the anode to the cathode in the wire, and transfer from the cathode to the anode inside the solution. Let's take an example for this electrolysis. Here we make electrolysis for zinc chloride molten. Here it is molten, not solution, and we will find a different gradient. When we have a molten, even the type of cations and the anion exist in the container will be to the salt only. So here in the container, we haven't any positive charged cation, even zinc, and we haven't any negative charged anions, even chlorine. So there is no competition at the two electrodes. We know that the opposite charge attracted to each other, so the zinc will direct it to the cathode, the zinc, which is positive charge, directed to the cathode, and take electron at the cathode, gaining electron at the cathode. So the zinc, which is positive charge, directed to the cathode, which is negative charge, and they take its electron and percept it at the cathode. We call the gaining electron from the previous lessons as reduction. So the process which occurs at the cathode called reduction, gaining electron. Always at the cathode we have reduction, which is gaining electron, and the opposite at the anode. At the anode, we have here the negatively charged chlorine, which is directed to the positive anode and losing its excess electron and neutralize it, changing into chlorine gas. So chlorine gas evolved at the anode because it's losing its electron, forming into a gas. So losing electron considered to be oxidation process. Losing electron considered to be oxidation process which occurs at the anode. So in the brief or the summary for this point, that anode is a positive charge where oxidation occurs, and the cathode is a negative charged electrode where a reduction occurs. So let's take an example. So let's take an example for electrolysis of the molten lead bromide. Molten lead bromide. What about molten lead bromide? Lead bromide, BB-Br2. So we have here, when it's molten, we haven't anything or any anions and the cations, even the lead and the bromine. We have in the container the cation of lead and the anion of bromine only. So there is no competition, only the bromine directed to the anode and only the lead directed to the cathode. The bromine, it will, at the anode, we say that we're losing electron. At the anode, we're losing electron and change into a gas. But at the cathode, the lead will gain its electron at the cathode, which is reduction process and perceived at the cathode. So the anode oxidation and the cathode is the reduction. This is the case of molten. Let's take a question. Why we can't make electrolysis for the lead bromide even it's molten? It's molten only which can make its electrolysis. So the lead bromide are insoluble salts. So the insoluble salts can't make electrolysis in a solution just with its molten. So let's see the difference when we have a hydrated or aqueous solutions. When we have aqueous solutions like NaCl, when we have NaCl molten, we say that is no competition. The positive directed to the cathode, the positive sodium directed to the cathode, and the negative chlorine directed to the anode. Anode is positive, cathode is negative. So the sodium will take the electron at the cathode, changing into sodium atom perceived at the cathode. This is the half reaction of the cathode. And the anode, chlorine, which is negatively charged particles, will lose its excess electron, changing into chlorine gas and releasing electrons. So it's losing electrons, so it's oxidation. This is for molten. What happened for the hydrolytic solutions when we electrolyze it? When we electrolyze hydrolytic solution, when the electrolyte will be aqueous solution, let's see the difference. Here we have positive, here we have negative cathode and positive anode. So let's see the difference. Be focused. We have Na at the cathode. We have Na positive of the sodium chloride, and also we have the water which hydrolyzed and ionized into H positive and OH negative. The water here ionized into H positive and OH negative. So at the cathode, we find that we have two cations, two positive ions, which competites, make a competition with each other to which one will be reduced, which one have the priority to reduce. At the anode, here, which is positive, directed the negative charged anions. We have here chlorine and OH. What is the rule of discharging each one of them? Let's take the rule. The rule of the positive ions or the cations is from the electrochemical activity series. From the activity series, as we go from up to down, the activity decrease, and the lower active elements, the lower active, it's desired to reduce. It is the better for reduction. The better for reduction, it is the lower active elements, and the higher active not reduced. So when copper meets the zinc in the electrolytic solution, copper will be reduced, not the zinc. When the hydrogen meets the sodium at the cathode, so the priority for the hydrogen to reduce because it's lower activity. That is the rule for the positive cation. And for the negative charged particles, we here have the sulfate, nitrate, chlorine, bromine, iodine, and hydroxide. From up to down, the ability of discharging at the anode increase. So the OH, it is the better one to oxidize at the anode. And the iodine, it is the following, and bromine, and eats on. So the ability of oxidation at the anode increase from sulfate, nitrate, chlorine, bromine, iodide, and hydroxide. So we can find here the hydrogen which will be reduced at the cathode, and here OH which will be oxidized at the anode. For OH will releasing electrons and forming O2 plus 2 H2O plus 2 excess electron. So it's losing electrons, so it's oxidation. That's anode. But at the cathode, hydrogen will desired to reduce by gaining electron, 2 electron. It is reduction, so gaining electron, and the change into hydrogen gas deposit. So that is the difference between molten electrolytic solution for NaCl and aqueous solution for NaCl. Later we will study the cases of solution, even the diluted or the concentrated one. Ask yourself, even the same result, it will be the same result if the solution will be diluted or concentrated or not. Let's take, for example, we have here in concentrated sodium chloride and diluted sodium chloride. We have in diluted sodium chloride Na positive, H positive, chlorine, OH negative, which directed to the cathode is sodium and hydrogen, but the hydrogen desired to reduce because it's lower in activity, and which directed to the anode, it's chlorine and hydroxide. According to the reactivity series for the negative particles, and hydroxide, which desired to oxidize and forming oxygen, that in case of diluted solution. But in case of concentrated solution, it's different. At the anode. At the cathode, it's the same result, but at the anode, the chlorine, by increasing concentration, it's desired to oxidize. So the difference in concentration, the chlorine take its opportunity to make oxidation and evolve it at the anode.